Okay, I think we can get started. Okay, welcome everybody. This is going to be the final week of our lecture series, and we're mainly going to close out the discussion on electromagnetic waves. So a good starting point is to basically recall what we've done last lecture. Here, what I want to start off with is basically reminding ourselves what are the wave equations for the electromagnetic field and also for the potentials. Okay, so let's start by simply noting that we have a so-called D'Alembertian, okay, which is simply given by a box is, depending on how you define it, 1 over c squared partial over partial t squared minus the Laplacian. Okay, and so using the D'Alembertian, you can very in a compact form, you can write down the so-called wave equation. And so let me ask you to remember what are the wave equations for the electric field in this case. You remember? So here I'm looking for the wave equation for the electromagnetic fields. Okay, I'm looking for the wave equation. Box V equals rho epsilon, not by selecting Lorentz gauge. So in this case, I'm actually looking at the electromagnetic field, so not at the scalar potential yet. Okay, last time we derived that as well. Do we remember that one? A hint, or at least a starting point. So indeed, the box operator, which is intimately connected to the wave equation. So here we're dealing with box E equals 2. Okay, you can get quite far by looking at the solution that Alex wrote down, so box V. In this case, the electromagnetic wave, the wave equation, simply minus the gradient of rho over epsilon naught minus mu naught. Very good, Schwan, I hope I pronounced this correctly, is the partial J partial T. Good job. Okay, and so similarly, we derive the wave equation for the magnetic field. And here we're looking at mu naught and the curl of J. Okay, now in this case, we can also write down the equivalent ones for the potentials. Okay. And so for the potentials, we're looking at potentials. There's something very similar. So we have box phi, which is a scalar potential, is just rho over epsilon naught. And similarly, we've got box A, the vector potential, such a way that we have not Now, again, in the time varying fields, bear in mind that the potential or the electric field is scalar potential, in this case, so-called of the electromagnetic field, is no longer just related to E, but there's also a mixing of A. Okay, do we remember what the definition is of the potential, of the scalar potential in this case, or the time varying fields? Okay, well, the origin of that, again, remember that the divergence of B in time varying fields remains zero, so the B magnetic field can be written as a vector potential. But in this case, E, the curl of E, is no longer zero. And so we can no longer write E simply as a negative gradient. But in this case, what we have, just right, so we've got negative of E, in this case, is given by uh, partial B partial T. So if this can be written as the curl of A, we can get the curl on that side. So something that E is equals to zero is, in this case, the curl of E, let's see, I'll get the signs correctly, so equals to zero. This, yeah. And then here, so E plus partial A partial T equals minus the gradient of phi. So in this case, E is just this case. E is simply the negative of phi minus partial A partial T. Okay. So indeed, my scalar field is now supplemented, or the gradient of the scalar field is supplemented by time varying field of A, the vector potential. But coming back here, this is correctly said. The fact that I can write this equation, I had to make use of a choice of gauge. Okay, in particular, I chose the Lorentz gauge here, which simply states that divergence of A plus 1 over c squared partial phi partial t. And remember, the choice of gauge stems from Helmholtz theorem. Right? We proved Helmholtz theorem, which states that any vector field can be written as the gradient or negative gradient of a scalar field and the curl of a vector field, provided that the divergence of A is specified. And so in this case, we've specified the divergence of A to be equals to this form here, so that we get a nice and neat wave equations for these. Okay, so today what I want to do is just like what we did for the Laplace equation. I want to take a specific look at the equation itself and the solutions to these equations. Okay, and so in that case, what I'm really after is first, again, writing them in the most generic form that I could think of, and that by itself should be quite insightful. So if I look at the uh, say second order PDE again. Again, this is only a subset of second order PDE. And in this case, let's consider A partial u. In this case, u is just any function, squared x squared plus b partial u partial x partial y plus c partial u partial squared equals to 0. In which case, these a, b, and c's are could even be functions of x and y, but in this case, we can also assume them to be constant. And we looked at this, this kind of style of equation before in the context of a two-dimensional Laplace equation. Can we recall two-dimensional Laplace equation simply this? 0, at least in Cartesian coordinates. This is two-dimensional Laplace. Okay. Now, similarly, if I look at the wave equation, I can write down the one-dimensional wave equation here. So I only have x, but now I also have 1 over c squared partial u squared partial t squared equals one-dimensional wave. And this wave equation in the absence of a source. So you can see that the two equations are related, right? They simply have a different c. The d is in both cases 0. There's no mixing between the partial derivatives, and then the c is different. It's simply one is 1 over one is just 1. The other one is minus 1 over small c squared. And again, just as a reminder, if I look at kind of the most general form that I could think about without even specifying the functional forms, I could assume a solution form, the following form, such a way that u x y equals f of p. Again, we've actually done this before for the Laplace equation, and now we're going to do, a little bit quicker, do the same thing for the one-dimensional wave equation. In this case, p is assumed to be a function of x and y. Okay. So I'm looking at a particular form to write u x y, so u of x and y, as a function of f, just a function of p. Itself can be a function of x, y. So very quickly, the partial derivative of u with respect to x can then be written as the total derivative f of p, partial derivative of p with respect to x. Okay. Again, similarly for y as well. And as we did before, we really look for a form of a solution. So we look for a solution that only depends on f dp squared, so that they can cancel out, and we get a simplified solution. So in this case, the partial p partial x has to be a constant. Because if it is not a constant, then when I take the second derivative of u with respect to x, I get extra terms there that I don't want. So in this case, again, I end up with p equals sum ax plus y. Okay, because here I just mirror the same thing as I do for y. And so by assuming p of this particular form, I can go ahead and solve it. I can write, for example, partial u, partial x is just A F dP, and then partial U, partial Y is just B F P. Okay, and I can take the second derivatives again. Partial U squared, partial X squared is A squared, and then the second derivative of F with respect to P, partial U, partial Y squared equals B squared dF dP squared. Finally, we have partial U, partial X, partial Y equals to A F. Okay, now here we still follow the same lines of reasoning that we've done before. So the beginning equation we wanted to solve, this equation over here, now simply has this following form: A squared plus big B small ab plus B squared F D. Now we're nearly there. So the solution for A and B, which simply states that A over B is just minus big B plus minus B squared minus 4AC divided by 2C. And these are equations for lambda 1 and lambda 2. Right? So there are two solutions to this, so in such a way that P1 is just x plus lambda 1y, and P2 is x plus lambda 2y. Okay. General solution is then given by U x y equals f x plus lambda 1y plus p x plus lambda 2y. Okay, so this is the most general solution to a second order partial differential equation of this form. Now, again, why are we going through so much trouble? And that's because we want to find the most general form for the wave equation. So for the one-dimensional wave equation, well, what do we have? Well, we have that A equals to 1, B equals to 0, big C equals to minus 1 over small c squared. In this equation here, this is just 1, and this is 1 over c squared, minus 1 over c squared. In this case, y is just the variable, it's just t. And in this case, we very quickly find that the equation that we need to solve is just 1 over lambda squared, 1 minus lambda squared over c squared equals to 0, so that L1 or lambda is plus minus c, also in this case. So P1 is just x minus ct, and P2 equals x plus ct. Such a way that the solution, the ux of t, in this case I've changed the variable to t now, here is simply given by some function x minus ct plus g x plus ct. Okay. And so even if we look at this equation, this solution over here, notice that irrespective of what f and g are, the general solution to this equation is given by a function that is only of x minus ct or x plus ct. And so what we can see is that this has solutions. In this case here, we have that same value for or for all. Just just going to do 4 points, and x minus ct is a particular constant, right? Because in this case here, f, I just consider f in that case, x minus ct is a particular constant, so that f is just the same function. So we get the same functional form, or the same position, same location, when I select this. And this is indeed, this here, this observer traveling at speed of light, or traveling at v. Okay? Because if you look at this equation over here, if x minus ct is a constant, then this is exactly the same. This is exactly the equation for someone that travels with a constant velocity. That velocity here is c. Okay. Now in this case, this is equation that travels at c, but in a positive x direction, and similarly x plus ct constant, which corresponds to this equation over here. There's g plus xct. It states that here we have observer traveling at negative x direction. What do I mean by an observer traveling in um, with v, right? With a particular v? Well, we're looking for solutions where they see the same thing. In this case, f. If the argument of f is a constant, then I see the same value for f. And so if I want to see the same value for f, what it means is then if I travel along, in this case with the wave, I see the same thing. So it'd be essentially the same as traveling alongside with the wave. And so indeed, the most general solution here is something that just travels along with the wave. In this one-dimensional case, you're either traveling with the wave, or you're traveling, in the x direction, or you're traveling one backwards in time. Those are two. Okay, but that's kind of more or less just even starting with the same in place where we looked at the Laplace equation, but now for the wave equation. Okay, now if I consider the 3D case, I have partial u x squared, partial u partial y squared, partial u z squared, minus 1 over c squared, partial u partial. So in this case, I could try the solution p is just L times x plus m times y plus n times z. In this case, well, let's do plus in such a way that now if I put this solution in here and I go through the same machinery to find the most general form, I end up with the equation L squared plus m squared plus n squared minus u squared over c squared times df dp. If I let mu simply equals to c plus minus c squared, sorry, plus minus c, then what do I have? I have that L squared plus m squared plus n squared equals to 1. A little. So in the three-dimensional case, what do I have? We have that L, M, and N are simply Cartesian components. Right? They multiply the X, Y, and Z. So these, if I take L, M, and N, are the Cartesian components. N hat is in the direction of the wave propagation. In such a way that now, if I consider this, I can write P as N hat dotted with R, right, where R is a position vector, plus minus CT. Full solution is just U as a function of R and T. Sum F N hat R minus CT plus P N hat times R plus CT. Okay. Similarly, in the three-dimensional case, the general solution is just given by a traveling wave in the direction of n is the direction in which it travels. So in the one-dimensional case, it's only x, but in this case, this is the three-dimensional version, and it does so at speed v constant that is here inside the wave equation, and either a forward wave in positive n hat direction or in the negative n hat direction. Okay, so that's the most kind of the most general solution to the wave equation. And I suggest that we take a quick break, and then we're going to take a look at how do we specifically write down the fields in such a way that we can deduce the properties of the electric field, of the magnetic fields. We'll look at the wave solution, but now specifically in the context of Maxwell's equations. Okay, so let's take a 5-minute break, and we'll come back at 5:08. Okay, everybody in a minute. Okay, welcome back, and let's continue our discussion. Okay, so when we look at the this wave structure, we see that we have a traveling wave, right? Traveling at speed given here by c, if we assume the equation of this form. And so one way to achieve that, when we refer back to the one-dimensional equation here. So the wave solutions, one-dimensional wave solution. Again, in one dimension, equation is just partial u partial x squared minus 1 over c partial u partial t squared. Okay, so in this case, what I can do is I could assume the form for f now, a specific form, and when we look at waves, typically functions that we are interested in are of a particular kind of waves. We can look at oscillatory functions such as the sine, cosine, p. Right? Again, where p in this case is just the solution that is proportional to x minus ct or x plus ct. So for waves, the typical familiar form is in the form of sine x minus omega t, right? Or cosine x minus omega t. And so, of course, I could also write in terms of in terms of complex notations. I could use the identity that I theta is the cosine theta plus I sine theta, in such a way that I know that the real part of e to the I x minus omega t is cosine minus omega t, and similarly the imaginary part, I kx minus omega t. Okay, and so when I'm considering, for example, cosines, I could still write it in the complex notation, let's say on this form, and just have to remember to take the real part of the complex notation when I'm considering the physical fields as opposed to some complex field, right? The electromagnetic field is a real field, a real vector field, and so in that case, we just we take the real part when I'm considering the final physical solution. But anyway, we could still, make use of the complex notation, complex form when we do our analysis of the waves. So let's actually take a look at, starting with an ansatz like this. So in this case, we have either sinusoidal or cosines, or we write it in the complex notation. Now, in the complex notation, what I have is that the time derivative, so time derivative partial by partial t of e to the I omega t minus kx. Again, it doesn't really matter where you put the minus sign. especially when we're considering cosines, the minus signs can just be taken. But here, what we have is I omega, right? We're just taking the partial derivative with respect to t. So we get I omega that comes out, and then we again get e to the I omega t. Similarly, partial x of I omega t minus kx equals minus ik I omega t minus like this. And so going back to this equation here, if I put this ansatz in here, I can now take the second derivative of u with respect to x and the second derivative with respect to t. So I would get these solutions, this one and this one, but just again getting one more factor out. So the wave equation the following yields that we get partial by partial x 1 over c squared partial by partial t operating on e to the I omega t minus kx. This given, which is equal to let's see, sure my negative sign. 9 here, negative a squared minus omega squared over c squared e to the I omega t minus like this. Okay. And so what we have in this case is that we end up, what we see here is we end up satisfying this equation now here. When when the inside here equals to 0, right? Because our equation simply states that this here on the left-hand side must equal here to the right-hand side. This, so what do we get? We get that this here should equal to 0. That's the way that c omega k. Okay. So we have now a so-called a dispersion relationship electromagnetic waves. You know how omega, or if you write it this way, omega equals ck. And if you remember from your past courses, function of omega, which is your frequency, the wave frequency, as a function of k is the so-called dispersion relation. Okay, now let's see where all of this brings us when we consider the electromagnetic waves specifically, right? We've looked at, in general, the properties of the wave, but in the sense of just the the general wave equation. But we know we can get extra information when we consider specifically the electric and the magnetic fields. Okay, so let's take a look there. consider the wave solutions for EM fields. In this case, we can write E just some E as a function of, let's say, K and omega, I omega t minus K dotted with R. Again, now we do it in full 3 dimensions. And similarly, B here, B omega 3I and omega t minus K. This. Okay. Now again, remember physical solutions are taking the real part of and the real part. Okay, where now in this case we've assumed E and B to be complex. Now in this 3-dimensional case, and you can see it back when we looked at the 3-dimensional here. Yes, the 3-dimensional case, we have this, vector K, which is just specifying the direction. And so what we can write similarly is that we have some K, generic K, which is just the sum squared of the K's in different directions, right? This is the wave vector in different directions. And we still have omega equals ck. But in this case, k is the square root of kx squared plus ky squared plus kx squared. Okay. So we're merely setting out the parameters, the expected solutions for now my wave equations for the electromagnetic fields. Okay, now let's take a look. Okay, so we have now the wave solutions, right? In this case, the most generic form of the of the solutions of the wave equations. And we want to see now what are the properties of electromagnetic waves. Okay, these are given by our equations here, right? Our equations here, especially when the right-hand side is 0, so this is in vacuum, will lead to equations that look like this. But nevertheless, we can still distill their properties when we consider the Maxwell's equations. So vacuum, of course, vacuum, Maxwell's equation are given by the following. And E, the divergence of E equals 0. Curl of E equals the negative of B, partial B, partial T. The divergence of B equals to 0. And the curl of B equals to 1 over C squared, partial E. And so we can now consider these solutions, right? Here on the top, the wave solutions in terms of the Maxwell's equations. Let's take a look. So first, we take this solution here, let's say the electric field, and let's say we consider this equation here, right? So the divergence of E equals to 0. Okay. So the divergence of E close to 0, well, that would be the divergence of E and omega to the I omega t minus kx. What was the convention I used here? Yeah, omega t minus. Three dimensions, so it's minus k dotted with r. Now the divergence is just the is the derivative with respect to r, right? To some position. It signifies, okay, what is the outflow, the rate of change in the outflow sense as a function of your position. And so we can simply write, when we have this, we can imagine this simply being a partial by partial r, but in a vector sense. And so what comes out rolling here is, in this case, a minus ik dot dotted with, again, right, as a function of a omega I omega t minus k dotted with r. Okay. Now similarly, that the curl of E is nabla cross a omega e I omega t minus k dotted with r. This again, now we've got nabla cross, and so again we're now looking at derivative with respect to r, so position vector r, so r vector, and but now in the curl, in the rotational sense. And so here again, I can just write I, k, but now the cross of k omega e to the I omega t r. Okay, finally, the partial derivative with respect to t of e. Here is just the partial derivative of e omega to the I omega t minus. So here we're taking the partial derivative with respect to t. That gives us I omega e omega dot is e to the I omega t minus k dot, like this. Okay, so we have now the divergence of E, the curl of E, and the partial derivative with respect to E. I can do exactly the same for B. Right? B is again given by the exact same structure, so B and E follow the same parallels. But now I can use all of this to put it into Maxwell's equations, and we can first look at, well, the divergence of E. Now just K times E, right? Because if I look at here, the divergence is just negative I K dot E, in which case if I take the here, I just get something that is A dotted with E, or proportional to, if you want to stick the i's and stuff in there. But the important thing is that this equals to 0. Well, okay, let me write it this way. So I know that the divergence of E must equal to 0. Therefore, by looking at this here, I know that K dotted with E must equal to 0. Right? This here is I. So indeed here I've got K dotted with E. And so immediately when I know K here, which is the wave vector in the direction of propagation, right? We've looked here. Actually, okay, here we've seen that indeed when I look at the three-dimensional case, I get this n hat dot r. Okay? So when I write it as k dot r, in this case, this is something that is in the direction of the propagation. And so when I look at this form over here, I see that k dotted with e equals to 0. What do I get? I immediately get that e perpendicular to propagation direction. Okay? So if the wave is traveling in, let's say, the z direction or the x direction, it depends on how you rotate your axis, the wave is simply going, the electric field is perpendicular to it. Okay? That is a pretty big result already. We know that the E field now is therefore a transverse wave, right? Transverse wave is defined to be where the effect, right, in this case, whether you take displacement or whether you take the field, is perpendicular to the direction of travel. Similarly, we know that the the divergence of B is also 0. And here we have A dotted with B equals to 0. So also B to the wave propagation direction. So we now have a system where B and E are transverse waves. This simply flows out of Maxwell's equation by assuming that the solution is of a wave solution or a plane wave solution. Now let's take a look at the other two equations. In this case, I get that curl of E equals 2. Well, let's take a look. Here the curl of E equals negative the partial derivative with respect to B. And so if I now take this here, this, then what do I get? I get that K plus E equals to omega B. Okay. So already from here, you can see that B is perpendicular to K is perpendicular to E. Let me write this in a clearer fashion. So K is perpendicular, sorry, B is perpendicular to K and perpendicular to E. but I already know that E is perpendicular to K. And so now what do I have? Right? I have a system where K, my wave vector, and then I've got an electric field and a magnetic field that are transverse with respect to K, with respect to the wave propagation direction, but that E and B are themselves perpendicular with respect to each other. And this is a pretty interesting result, right? So, we now know if I have a plane wave equation, how does the E field and the B field operate? How are they related to each other? Okay, now the final Maxwell's equations give us, in that sense, no really new information. So here I've got the curl of B equals 1 over C squared E partial T. And so in that case, what do I get? I get that this one partial E, I get that. I get that here. I get minus, sorry, A cross B omega over C squared. And again, this gives us the same picture where E, B, and K are mutually perpendicular. Now, there remains only one final thing to consider, and that is specifically in which what are the ratios of the fields, and that we can simply take a look at. For example, I could take a look at, for example, the following equation. So if I take to recall that have that A cross E, okay. But now if I do E dot this, now this must be equal to 0 because the resultant of K cross E must be perpendicular to E. And so if I just do E dot here, I must get something that equals to 0. And so here I get, sorry, what I meant to do was cross here. So this here, when I do E cross K cross E, I get that this is something that is K squared. Okay, because K and E create something that's perpendicular to both E and K. And if I do E cross again, I get something that is of this form. But I know that A cross E equals omega B. In this case, here again, we know that this equals to omega E cross B. Okay, so in this case, we can simply arrive at something that looks following form. Get that. Yeah. In this case, we get that. Correct. So I get that k squared equals omega b. I know that a over omega is just 1 over c. In this case, I have something that looks like squared 1 over c equals cross. Just the same direction as e. Okay, because here I'm just taking the magnitude. The magnitude of k divided by omega is just 1 over c. Here I'm just taking the magnitude of both fields in such a way that I basically get the following. Get that. I get that. The magnitude of b equals 1 over c of the magnitude of e. Okay, so simply by having the wave solution, plane wave solution, and plugging them back in to Maxwell's equations, I can end up deriving the properties of the electromagnetic waves. And in particular, these are one, M waves are transverse waves. Transverse waves in such a way that A is perpendicular to the E field and K is perpendicular to the B field. Okay. And wave is the K is the wave propagation direction, or proportional to the wave propagation direction. Also know that that in particular, know that K is proportional to E cross B. So this gives you the handedness of K, and then you can actually see that from this equation over here. So we know that K and E and B are mutually orthogonal in the directional sense that E cross B is in the direction of the wave. And finally, 3 magnitudes are given by equals to the magnitude of over C. Okay, so simply by looking at the wave equation, wave solution, and putting them back into Maxwell's equations, we end up with these three properties of the electromagnetic waves. And we have the final one. We actually have to go back all the way to the wave equation here. This I actually never written it down. Okay, so in this case, yes, the wave equation here, in this case, identification that epsilon naught is 1 over c squared. So, if you will, there's also a fourth property, travels at velocity 1 over the square root of epsilon naught mu naught. You know, this is a remarkable result, right? We've basically shown simply by going through the time-dependent equations of Maxwell's theory that we end up with a wave solution where the wave velocity, the wave speed, is simply given by two fundamental constants, epsilon naught mu naught. And moreover, we have the exact structure of the wave, all spelled out. Okay. Now, why is this important, and why is this so fundamental? Because when we assumed, let's see, we have here we go. First equation, very first equation. So here, even in vacuum, right, when the right-hand side of these are zeros, which is the wave equation that we ended up solving, right? We ended up solving it here. This wave equation here. So the right-hand side is 0, which is the corresponding case for vacuum. And so in vacuum, there are actually solutions that travels, that propagates as a wave without any source. Right? The right-hand side is 0. So no rho, no j, and we still end up in Maxwell's equations with solutions for waves traveling at some finite velocity. And so if you will, any disturbance, any change in the electromagnetic field propagates at exactly this velocity, at this velocity over here. And this is a constant. Okay? So this does away with all this, basically interaction, instantaneous interaction at a distance. The electromagnetic field propagates as a wave with a finite velocity. Okay, so this is a good moment to take a quick break, and after the break, we're going to come back and we're going to take a look at what happens if I now change these equations into matter. Right, this is what we did before. So what happens in matter, and in particular, what happens to the electromagnetic waves when they cross the boundary between different matter, different materials. Okay, let's take a 5-minute break and we come back at 5:53. Okay, guys, in a bit. Okay, welcome back. I see that there is a question regarding the why can del dot E be dot E? Okay, let's take a look at the answer to this. In this case, in particular, what we're looking at is as follows. So we first have to note that we can write E in this form, right? And so what I'm doing here, this form over here, simply writing k dot r as kx times x y in the y z z. And so when I'm taking the nabla dot, okay, nabla dot e, in this case, this nabla partial x partial y partial z, right, in Cartesian coordinates. And so here I'm simply I could do this in turn, right? I can take partial partial by partial x of e, in which case I get kx y, because here I'm taking e to the I this. And so I get I times, and this is minus sign here. And for each of these, I'm getting the x, k, y, k, z. Therefore, this is therefore the equivalent of minus I, k. Is that clear? Alex, Manchu? Okay, I mean, if it's not clear, please ask. I somehow had assumed that this was actually you had seen this before, but if you haven't, that's fine. But this is here. Really, it's just taking the x component partial by partial x, the y component partial by partial y, and the z component partial by partial z. In which case, I can simply write kx y kz dotted with x y z. Okay, and therefore it's k dotted with e. But again, this all hinges on assuming that we have the solution as a wave solution, as a plane wave solution, that this works, right? In general, if E is not of a wave solution, this doesn't work. Okay, so only when when E can be written of this form, it can be written of this form here and here. Okay. So let's move to the last bits. Okay, the last bits and portions. In which case, this is I just want to show what happens when we're looking at materials in when a wave travels through a particular material. And when a wave travels into a particular material, what can we deduce from it? And so I could, I could write down Maxwell's equations. Maxwell's equations. Okay, or time varying fields now. Maxwell's equations, time varying fields, but now in matter. In which case, what I end up writing, what I can show is that this is the equation that we've seen before. So this is the divergence of D equals to 0. The divergence of B equals to 0. The curl of E equals to minus B. And no free charge occurrence. And finally, we can write H as partial D. Okay. So you'll get this set of equations when you transition into matter. It should be fairly straightforward to show. And so in this case, when we are having the medium, again, we typically assume that the medium linear and homogeneous material. Simply epsilon E and H 1 over mu B. Okay. In such a case that when these are constants now, the epsilon and 1 over mu are constants, then we can write down Maxwell's equations is here. The curl of E, this one, and the divergence of B equals to 0. And curl of B equals to, now in this case, mu epsilon partial E. Okay. In particular, what do we have? It's simply the replacement of mu naught goes to mu, and epsilon naught goes to epsilon. This is something that we've seen before in the past. We discussed materials. And so, especially when we talk about a medium that is linear and homogeneous, we end up with a system where everything's the same except for this contribution here. So if we compare this set of equations, which will put with what we started off with, which is, write them down somewhere. Okay, that's fine. But in the time varying field, the only difference is that now here we get that mu naught epsilon naught is going to mu epsilon. And so we end up having the same equations, the same wave equations, except that the wave velocity changes. So in the linear and homogeneous material, end up having the same wave equation in linear and homogeneous materials. Except that the velocity, the wave velocity, let's call this v now, is 1 over square root epsilon mu. This here is, you can write as c over n. N is now epsilon naught mu over epsilon, sorry, epsilon mu over epsilon naught mu naught square root. And this n, it turns out, is simply the index of refraction that you've actually seen in materials. Okay. Now there is a way to show this, but that will go beyond the scope of this this lecture course. But I just wanted to show you that where this, when we've seen in optics, index of refraction is simply a number that is given. It's actually the wave velocity for different materials. So when we determine experimentally what mu is and what epsilon is for linear and homogeneous materials, we actually end up getting a value for the wave velocity where n, which is the relative velocity with respect to the speed of light, in this case, is simply the same as the refractive index. So the whole system, when we talk about materials, is exactly the same, with only one notable difference, and that is the refractive. And so in this case, what we can do, and I'll have you derive this in one of the problem sets, is that you end up, when you travel from one boundary, when you have a wave going from one medium, right? Inside the medium, it's simple. It's just the same wave equation with just a different wave velocity. But when we are going in across media, then something happens, right? The wave velocity changes, but we have the tools to take into account for this, which is actually given by the boundary conditions. Okay, so recall, and boundary conditions basically specify that across boundaries, that epsilon 1 perpendicular is epsilon 2 perpendicular. And that would be 1, right? On one side, perpendicular is B2 perpendicular. And 3 is that E parallel is the same parallel. 1, 2, and 4. B parallel. One over mu1, B1 parallel 1 over mu2. Okay, so when we talk about matter, end up with exactly the same situation, and we also must adhere to the electromagnetic boundary conditions. And so one of the things that I'll have you do, what I'll have you derive in the in the problem set for this week is what happens when an electromagnetic wave in a medium travels in between media, right? When it transitions from one medium to. Okay, so that's pretty much all I wanted to say. And I would even go as far as saying that this pretty much wraps up the end of most of, sorry, this wraps up everything I really wanted to say in terms of the course. Next lecture, which is going to be the final lecture, I want to spend just a little bit of time. We'll do a recap, maybe a big overview of all the key concepts, but also I want to take a look ahead what you may expect in 4041 in terms of moving towards relativity, moving towards more advanced applications. But for now, for today, this is what I wanted to say. Let me open up the floor to see if there are any questions. Okay, so there's a question in this case from Leung Chun Hua, asking why is k in the direction of the wave? Okay, so remember we started off when we derived the most general form of the wave equation, and in this case here, and so when we do it in 3 dimensions, here we can see that when we have this form, which is a 3-dimensional wave equation, then we end up seeing that L, M, and N, right, in this case, in our most general form of the solution, is simply the Cartesian components of some unit vector n. Such a way that I can write the form here n dotted with r. So this is simply specifying how much x, this wave, how much x, how much y, how much z there is. So in this case, this is simply giving you the to which extent there's an x component, there's a y component, and a z component. And so here we know that this n here is the is a unit vector in the direction of the wave propagation, right? Because we end up being able to write the wave in this form here, this n dotted with r. Okay, the second question here is velocity EM slow down in matter. Does it contradict with relativity? As relativity states that speed of light is always. So indeed, Chan Ai-hin is saying it should be constant in vacuum, and that is correct, right? Speed of light is always constant. It refers not to when we look at different materials, but it refers to different observers. Okay? So when a different observer, when I move with a particular velocity, this is very, very curious. When I move at a particular velocity, I will still see the wave equation with exactly this number here. That was really what set Einstein to think. How is it possible? any velocity that I move in, I still get the same wave equation. So the speed of light, right? Because this gives you the speed of light. It's the same for all observers. So it's constant with respect to observers, but not constant with respect to the material. So again, Chan Kai-hin is asking, is it because the path has changed? There is a longer path in matter. Okay, I don't want to give too much of a classical. Yes, in a classical sense, you can say, okay, maybe the path has changed. Um, yes, so indeed, Pun Shun Chi is indeed correct. In order to give a semi-satisfactory answer, we have to look at quantum effect. And so, I could give you an analogy, exactly what happens there, at the quantum level. But I fear that whatever I say, maybe an analogy that could be misinterpreted. So I don't want to go to that level. But if you want to really see what happens, right? Because if you look at the level of paths, then you're really considering individual photons. For that we do need quantum electrodynamics or quantum field theories. So I want to defer the physical picture of what happens to an individual photon to almost graduate level courses. I don't think you'll even get a satisfactory answer in 4041. So Jason is asking if there's no phase shift between E and B waves, would the energy density be conserved? Okay. Let's see. Is that a necessary condition? There's no phase shift between E and energy density be conserved. In that case, no. Because if there's no phase shift in between, if they both have the same phase, then the energy density, which again is beyond the scope of this course, you would end up with an oscillating density, right? When the electric field goes to zero, and if the B field also ends up being zero, then at that point you'll have zero. So no, and in fact, you end up seeing that they must exactly be out of phase with each other, so that you can recover, the same, energy density of the wave going through. But again, that's a little bit beyond the scope of this class. This is exactly the material that you'll get, like the energy density of waves, and in which direction it points, like the Poynting vector for the electromagnetic wave. So which direction does the energy momentum of the wave go? That's something that you'll get in 4041. So Jeffrey's asking, is the value of mu naught and epsilon naught a consequence of the finite speed of light? This goes a little bit in the realm of philosophy, as opposed to, because then you'd have to ask, okay, what happens if the speed of light is infinite, or at least is not a constant for everyone? Um, for the application or level of this course, I would say this is value, mu naught and epsilon naught are experimentally verified values, right? And they are experimentally verified constants. And this has to do with just, okay, when we define a unit charge, how much force and how much things are there. That's that. And the same with mu naught. And those two values, mu naught, epsilon, that end up setting the velocity, the wave velocity of the electron. When the precise values of those is I mean, they're constants of nature, right? I'm very reluctant to say, is it because of the finite speed of light? All that we know is that the finite speed of light makes it that the epsilon naught and mu naught, the product of those two, must equal to c exactly. But fundamentally, it is what we measured, right? We put a unit charge somewhere, and we look at, okay, how much force does it have on another charge? So if you're a physicist, and I would say not a kind of a physical philosopher, that is your guiding principle, right? This is what we measure, and so we must adhere to that. This is what experimentally comes out, and then we use mathematics to describe it. So I'm very reluctant to attach what is the consequence of what. I would say from a physical perspective, the values of mu naught and epsilon naught, because they're constants, end up giving us a system where the electromagnetic waves travel at a constant speed of light. But that's more or less because of the historical sense. If we had experiments where we could measure those waves first and then determine the values of these constants to be of a particular value. In other experiments, we would have maybe turned it around in the other way. But one implies the other, whichever one comes first is, from the physical perspective, just the order in which all these experiments were done. Right. So Isaac is indeed saying historically, c computed from mu naught was found to be consistent with the speed of light. And that's where that suggestion of the speed of light, that light is an electromagnetic wave. That's right. So Jeffrey, even that, right? When we think about massless particles and the photons, and that really goes also in the realm of quantum physics and so on. But that was not really the original thing. Right? The original thing was the following: is that c, so the waves, electromagnetic waves, travel at a particular speed, and we found that light travels at the same speed. And so that was really where the two were thought to be connected, right? That an electromagnetic wave is light. And whether we can translate this to all massless particles travel at the speed of light is a development that came later. Okay, any other questions or comments? Recording then.